Hi, Mr. Richards here. Today's lesson is on recursive formulas. And we need to ask ourselves, what is a recursive formula? Well, a recursive formula is a formula in which each term is formulated from one or more previous terms. Basically, this means we're going to need to look at previous terms in order to get our next terms. So when we're asked, find the first 5 terms of the sequence. Now let's break this down. A1 equals -8. This A with the 1 means this is our first term. So our first term is -8. Now for our formula, this says, and any term equals -2 times an minus 1. This means the previous term. So -2 times the previous term plus 5. Now, let's make ourselves a table here. We'll have our first term, our second term, our third term, our fourth term, and our fifth term. Now, our first term is easy. That's just listed as -8. Now to find our second term, we're going to say, well, our second term, so A2, that's our second term, is going to equal -2 multiplied by whatever our second minus 1 term is plus 5. What does this all mean? -2 multiplied, 2 minus 1 is 1, so A1 plus 5. So what in the world does -2 times A1 plus 5 mean? Well, A1 represents our first term. So we're going to take, to find the second term, -2 times the first term plus 5. So -2 times the first term was -8 plus 5. -2 times -8 is a positive 16 plus 5. And 16 plus 5 is 21. So our second term is 21. What about the third term? Well, to find the third term, we're going to use the same formula. -2 multiplied by A, then to the 3 minus 1 term here, plus 5. Well, the 3 minus 1 term is simply the second term. We're going to take -2 then times the second term, which is 21. So -2 times 21 plus 5. -2 times 21 is a -42. Plus 5 is -37. Now for the fourth term, we're going to take a look at -2 times the previous term. Now, 4 minus 1 is 3. So we're looking at the third term, which is -37, and we're adding 5. -2 times -37 is 74. Plus 5 will get us to 79. And lastly, for the fifth term, we're going to take a look at -2 times our fourth term, which is 79, plus 5. -2 times 79 is -158, plus 5 then is -153. So, what are the first 5 terms of the sequence, -8, 21, -37, 79, and -153. And if we look back at our definition of recursive formula, each term is formulated from one or more previous terms. We had our first term. To calculate our second term, we had to look back at the first in order to calculate it or formulate it. And the same thing with the third. To find the third term, we had to look back one to the second in order to calculate it. Fourth term, back to the third. Fifth term, back to the fourth in order to calculate these. And this is what recursive formulas are all about. In example 2a, we're being asked to write a recursive formula for the sequence. And here we have the steps to writing recursive formulas. Step 1, determine if the sequence is arithmetic or geometric by finding a common difference or a common ratio. If there's a common difference, we're arithmetic. Common ratio means we're geometric. Well, let's look at 23, 29, 35, 41. It looks like from 23 to 29, I can say, well, I'm adding 6. Does this continue? From 29 to 35, I'm adding 6, and from 35 to 41, I'm adding 6 as well. So this is an example of an arithmetic sequence. So we can then look at step 2, write a recursive formula. For arithmetic sequences, we can write this as an, which is any term. We're going to look at the previous term and add this common difference. All right, but we always need to start with that first term. And so we're going to say our first term, A1, is equal to 23. And again, we're going to use this right here. an, so any term, is going to equal an minus 1, the previous term, plus 6, our common difference. And then we're going to write n is greater than or equal to 2. And this is our recursive formula for the sequence 23, 29, 35, 41. And in case you're wondering, what is it with this n is greater than or equal to 2 business? Basically, we're given the first term. If we stick the 2 back in for this n, we're looking for the second term. That means we're looking to calculate the second term. 2 minus 1 is 1. So we're going back to the first term in order to calculate. If this number was 1, if we're looking for the first term, then 1 minus 1 here would be 0, and we're looking at term 0. Well, we don't have a 0th term. So the only place we can go right now is back to the first term, which is why our n has to be greater than or equal to 2. Now, 7, negative 21, 63, negative 189. Well, as we're going from positives to negatives and negatives to positives, we're not adding or subtracting anything here. We don't have a common difference. So this is not going to be arithmetic. Most likely it's going to be geometric. And if we look from 7 to negative 21, how can I do that? Well, you can multiply by negative 3. From negative 21 to 63, I again can multiply by negative 3. And from 63 to negative 189, I'm again multiplying by negative 3. So this is an example of a geometric sequence, which means we're going to be looking right here for our formula. We again start off by writing our first term. So our first term, A1, is going to equal 7. And then we can say for any term, an, we're going to now look at our ratio and multiply. So we're going to say multiply by negative 3 times our an minus 1, so negative 3 times our previous term. And then n is going to be greater than or equal to 2. And even if we were just to test this answer, let's mentally check this. Say you want to find the second term. Well, we know the second term is negative 21. And so put this in. We're going to look at the first term and multiply by negative 3. The first term is 7. 7 times negative 3 is negative 21. Neat. What about the third term? Well, we're going to look then at the 3 minus 1, so the second term. The second term is negative 21. Negative 21 times negative 3 is a positive 63. So we wrote the correct formula. In our next section, we're going to be asked to go back and forth between recursive formulas and explicit formulas for both arithmetic and geometric sequences. So what I'd like to do is give us both sets of formulas here in order to help us out. So if we have an arithmetic sequence, and remember that's when we are having a common difference, what we can do if we're looking at a recursive formula for this, this is when we look for the first term, A1. Then we're going to have, for any term, we can look at the previous term and add the common difference as long as n is greater than or equal to 2. Now what happens when I want to take this recursive to something that's explicit? Well, we have a formula for this. For any term, we can look at the first term and add this n minus 1, which is kind of looking at that previous term idea again, times our common difference. Now, what about geometric? Well, geometric, remember, we have our common ratio with these. And recursive for these, we're still going to have our first term. We're going to be looking for any term. We can take our common ratio, r, and multiply it by the previous term, as long as n is greater than or equal to 2. Then for explicit, for any term, we can look at our first term and multiply it by our common ratio to the n minus 1 power. So that previous term idea again. And so here you have the recursive formulas for both arithmetic and geometric, and the explicit formulas for both arithmetic and geometric. Hopefully you can use those formulas to help you on this question. The price of a car depreciates at the end of each year. A, write a recursive formula for the sequence. And B, write an explicit formula for the sequence. Before we can do that, we need to figure out whether or not we have an arithmetic or a geometric sequence. Well, if I list my numbers out, 12,000, 7,200, 4,320, and 2,592. Let's look to see if I have a common difference first. Well, if I'm going from 1,200 to 7,200, I'm subtracting 4,800. But if I'm going from 7,200 to 4,320, I'm only subtracting 2,880. So I do not have a common difference. I need to look for a common ratio. So if we take 7,200 and divide by 12,000, we're going to get 6/10. If we look at 4,320 and divide by 7,200, I once again get 6/10. And just for good measure, if I look at 2,592 and divide it by 4,320, I once again get 6/10. So I have a common ratio, which means I have a geometric sequence. So, in order to set up the recursive formula first for part A, we can go back into our geometric idea. So our first term, A1, is equal to 12,000. And then, to find any term, AN, we're going to look at this common ratio, so 0.6 or 6/10, and multiply that by our previous term, a n minus 1, as long as n is greater than or equal to 2. And lastly then, for our explicit formula, we can use the idea, once again, from the previous slide here, that any term, we're going to look at the first term and multiply it by our common ratio to the n minus 1 power. We can fill this in by saying an is going to equal our first term of 12,000 multiplied by our common ratio of 6/10 to the n minus 1 power. So we have our recursive formula for the sequence in part A and our explicit formula here in part B. In example 4, for each recursive formula, write an explicit formula. For each explicit formula, write a recursive formula. Well, since we're already at an and not this whole first term and an business, we already have, right now, an explicit formula. So we need to take this from explicit to recursive. Now, explicit formulas can either now be geometric or arithmetic. The geometric ones had the exponent to the n minus 1 power. So this is simply arithmetic right now. And so what we need to be able to do is to write this in the form, all right, I have my first term equals something. Then, for any term, we're going to look at the previous term and add the common difference as long as n is greater than or equal to 2. Well, first we need to find what that first term is. So if I look for my first term here, all I need to do is put 1 in for n. So 2 multiplied by 1 minus 4. That's 2 minus 4. So my first term is going to be negative 2. So A1 equals negative 2. Now, in order to help myself find this common difference, a couple different ways to go about this. One way is to look for the second term and see what changed. Well, for my second term, I can take 2 times 2 minus 4. That's 4 minus 4, which is 0. So the second term is 0. How'd I get from the first term to the second term? I added 2. So my common difference here is going to be adding 2. So I can finish this by saying any term, I can look at the previous term and add 2 as long as n is greater than or equal to 2. So first, We recognize we're going from explicit to recursive. We recognize that we're already given arithmetic. So we need to find the first term, which was -2. For any term, then we need to find what our common difference is. We did this so far by looking at the second term and comparing it. Oh, look, I added 2 to it. The other way, right there, that little 2 also tells you what your common difference is going to be. If you can't remember that, though, just find what your second term is and see how you went from your first to your second. In example B, we're given the first term is 84. For any term, multiply the previous term by 1.5 and add 5. Well, this is an example of a recursive formula. So here we need to go from recursive to explicit. And since we have this little multiplication thing here, this is considered a geometric sequence. So to go from recursive to explicit, we can use our formula an equals our first term multiplied by our common ratio to the n minus 1 power. So for any term, we can look at our first term, which is 84. Then, to find this common ratio, it's this 1.5. So 1.5 to the n minus 1 power. And that is our solution. Now, in order to summarize this lesson, I would like to give us an example of another sequence here. So we have 8, 18, 28, 38. Now let's identify what this sequence is. It looks like, and we are indeed, adding 10 to each previous term. So this is an example of an arithmetic sequence. And to write an arithmetic recursive formula, we are going to use the first term idea, and then for any term, we can look at the previous term, an minus 1, and add our common difference as long as n is greater than or equal to 2. And so to fill this in, our first term is 8. And then for any term, we'll look at the previous term and add 10 as long as n is greater than or equal to 2. And that is our recursive arithmetic formula for this sequence. Next, if we want to look into explicit for the arithmetic sequence, we will look at any term equal to the first term plus our n minus 1 multiplied by d, our common difference. So for this requires a little bit more work. We have our first term at 8 plus our previous term, n minus 1, times d, our common difference of 10. Now this does require a little bit of distributive property in order to simplify. And so an is going to equal 8 plus 10 times n is 10n. 10 times the minus 1 is minus 10. And now we need to look at this 8 minus 10 and simplify it. So an is going to equal our 10n, and 8 minus 10 is minus 2. And that is our arithmetic explicit formula. Lastly, what if we had the sequence 8, 48, 288, 1,728? Well, from 8 to 48, we're multiplying by 6, so there's a pretty good guess. From 48 to 288, we're doing the same thing, and in fact, we are. 288 to 1,728, we're also multiplying by 6. So this is an example of a geometric, since we have a common ratio. To do a geometric recursive, we're going to look for the first term and say for any term, we're going to multiply that common ratio by the previous term, as long as that term number is greater than or equal to 2. So to fill in for this one, our first term is equal to 8. In order to find any term, we're going to take our common ratio of 6 and multiply it by the previous term, as long as n is greater than or equal to 2. So that's our recursive geometric formula. And then to get this to be explicit, we can use the form for any term. We're going to look at the first term and multiply it by the common ratio to the n minus 1 power. So for any term, it's going to be our first term of 8 multiplied by our common ratio of 6 to the n minus 1 power, and traditionally this is written with the parentheses, so 8 times 6 to the n minus 1 power. And that is our explicit formula for geometric sequences. And that is it for this lesson on recursive formulas. Good luck.